All right. So what we have is a pressure compensated system to talk about today, and this stepping stone for a load sensing system. All right, pressure compensated system. I need to have a closed center DCV, and I threw myself in a actuator behind that, a pressure differential cylinder. But looking back at, I got a gauge to measure flow, and I got a pressure gauge and a gauge to measure flow, and I have a pressure gauge over here. But let's look at what's actually in the pump. So really, if I was to look at the pump, I have this thing up here, which is known as a bias spring, and it has one job. There's a spring in behind a piston to physically try and control this particular angle. So this might be my swash plate in this particular pump, and it's trying to increase this swash plate angle on this. We'll call it an axial piston pump. So here's my hydraulic pump. It is on maximum swash plate angle. It's capable of 100 gallons per minute if I was running, say, 2,000 RPM. So it's a pretty good sized pump. And so hydraulic pump, there's my swash plate angle, a bias spring, and then it has one job to produce flow. If I actually hit the key, it should be on produce flow. So at 0 RPM, it should be on maximum angle. If I hit the key and that pump produces flow, there's no place for the flow to go with this closed center DCV. Pressure gauge, that's nice. And no place to go with this valve down here. This I've drawn it as a 2-position valve. So this is the brains for the whole thing. This is what tells this pump to do this. So what do I have? I had a bias spring to say, hey, spring to try and maximize flow. And then I had a servo or a stroking piston, which was here to overcome that spring and actually de-stroke the pump, is referred to, if the situation was bad. And the situation would obviously be very bad if I hit the key, produced flow, no place for it to go. And if I only used a relief valve, as in just put a system relief valve in here instead, then all that 100 gallons per minute would be going over, say the relief valve's a 6,000 psi's, then 100 gallons a minute is going over the relief valve. And I'm pretty sure you're going to burn up the oil in the system, and you're probably going to change the color on the hydraulic tank as well. You didn't like that color of paint anyway. Brown is a much nicer color. That's not a good thing. So here's what we do. We're going to put in an automatic control valve that says, hey, if you hit the key and there's no place for that oil to go, then I'm going to register what would have been 0 psi, did before I hit the key. I'm going to register whatever pressure is on that or load on that pump, and well, it was blocked. I'm going to register that pressure right here and physically work against this spring. So the spring is trying to hold this pressure compensator valve up. I'm going to give it a name, pressure compensator valve, and I'm going to give it some resistance. I'm going to put a 6,000 psi spring force on the bottom of this, and it will hold it up by about 6,000 psi. In other words, it would take 6,000 psi here before it physically overcomes it, and when it overcomes it, this is what happens. I start at 0, I hit the key, and this pressure will climb all the way up until it hits 6,000 psi. I'm sticking with imperial right now. As soon as it hits 6,000 psi, or for some people who are really technical, 6,001, but you've adjusted this to 6,000. So as soon as it hits 6,000, this is what it does. It switches and moves this red envelope down in line with these connections over here. So now what was open to tank is blocked, and what it does is it takes pump flow and it sends it this way, which physically comes in behind this piston and takes that piston and runs that piston all the way up to here someplace, taking the rod connection and physically will de-stroke that pump. And it de-strokes it all the way maybe down to about 2 degrees, and it takes this rod that was in here and it physically physically takes that rod, that piston that was in here, and it shoves it all the way down to the bottom end of here, now compressing that spring, providing I could actually make sure it's not hydraulically locked. So that's kind of the clue to this, is we want to make sure that this isn't hydraulically locked out the back end of it. Otherwise, bad things could happen as well. So there's a spring in there, and that's referred to as my bias spring. So that's kind of the start of it. And the pump destrokes, and it only produces enough flow to maintain the 6,000 psi in neutral standby. So that's a terminology you want to understand, and it's also a terminology you want to understand if you're going to test this particular system, because it requires me to maintain 6,000 psi in this gauge in something referred to as neutral standby pressure. You're going to hook a gauge up to a system, you better know what kind of a system you're going to be running, because if we had an open center system, pump flow just going through the tank, I would expect to see 0. But when I hook a gauge into this system and hit the key, this is not 6,000 or 0 psi anymore. This neutral standby is sitting at 6,000 psi and wanting to go someplace. And if you put a 100 psi gauge on it, I'm pretty sure it's willing to go right through that gauge. So that would be a bad thing. So, as soon as you fire up the key, pump's trying to go someplace, produces enough flow until it hits 6,000 psi, which is right now, because really, this is maybe just a little 1-inch piston in here that travels a couple inches. That is instantaneous almost. So, and it produces enough flow to maintain 6,000 in here. And I say it doesn't go to true 0 because we always have this internal leakage in a pump, this case drain to keep up with. So it's producing enough flow to keep up with this. And really any other internal leakages, like if I had a little bit on the DCV, which we realize does happen, but it's so minute. If I was going to put a flow meter in here, you would not be able to read that unless you had a very, very extremely accurate flow meter. And you'd be challenged to read it at the low end just for the accuracy of the flow meter if you look up the specs. So for all practical purposes, closed center, 0 flow going through the DCV, yep, done. However, you got a little bit of flow just going through here to control this stroking piston to de-stroke that pump. Just enough flow coming out of the pump to keep up with some leakage here, which ultimately is all built into this housing, which is all going out towards the tank over here. I just drew it as 2 separate ones. So that's kind of the concept of how this starts. And if we were going to try and move our actuator now, so we put an actuator on here, and if there was no load on it, and I had 0 psi, so if I had no load on this, then one of the next terminologies you want to know is, well, what makes this pump upstroke automatically? If it's an automatic system, I can see how it de-stroked, but what made it upstroke automatically? Okay, so here's what I'm going to do. I'm going to try and lift this load, which there is no load. It says 0 psi sitting on the bottom of this cylinder, so it's just there. So I'm going to try and lift it. Here's me moving the DCV now. So if I move this DCV to deliver pump flow straight to here, we can see already I had 0 on here. Therefore, this solid line through the DCV, if I was to measure it here, it should say 0. And if I measured it here, the same solid line to the pump, it should probably say 0. Probably. And by probably, it will. As soon as you move that, fully open it, that should drop to 0. And 0 versus 6,000. Pretty sure I know which one's going to win. Now my spring is strong enough that this particular envelope actually shuttles back up again. And when it shuttles up, it connects, first off, it blocks the pump flow that was going to here. So I'll get rid of the pump flow that was going to that. The pump flow that was actually going to that is gone. And I'm actually going to connect this inside of here, all that oil that was in there, all that oil that was in here, trying to force that piston to destroke the pump, is now connected right back to tank. And we know there's no pressure on the tank, so it's connected back to tank. So, well, I still haven't actually destroked it. All I've given it is the chance to destroke it, and therein lies the bias spring. The bias spring, which we have compressed down to a lot of force, says, hey, nothing holding me back anymore. Woohoo! So now that bias spring, it will upstroke back to that full 20 degrees. If I fully open this, then that kicks in and upstrokes, shuttles this obviously down. So now my swash plate angle is back to my original angle. And what was destroked before, what was actually destroked before, is now changed completely, because the spring said, hey, I can breathe, great, and let it go, and it will physically take that piston and it will shove it all the way back here someplace and squeeze in all the oil out to tank. Yep. And now my pump produces maximum flow. Just let her go. So this is upstroked now right to whatever the pump's capable of. So we've seen it start, we've seen it destroke, and we've now seen it upstroke. And it's fully upstroked. Sounds fair? And as far as I'm going, I had no load on this. So if I just put start to put a load on here, and the load I throw on here is, oh, I don't know, maybe 2,000 psi. If that's 2,000 psi, then is that enough to overcome this spring? If I had 2,000 there, then I should see 2,000 over here. So if I have 2,000 over here, I'm starting to load this pump up, but isn't enough to overcome this spring. And I think we can agree that 2,000 versus 6,000, I'm pretty sure this spring wins. And the pump is just producing the maximum flow you have there. And that will happen right up until I start stacking loads on here, and I keep stacking loads on here until ultimately the maximum load I will ever send on here, if I stack one brick on there, then I'm at 4,000. Life is good. Pump's saying, hey, 6,000 psi spring. I don't care if you increase the load up to 4,000 psi. I'm good to go. It's when I keep stacking a load on there, the maximum I will ever see here is 6,000. So the most I can see here is 6,000 psi. And once I hit 6,000, then that's the maximum flow I can create. And what will happen is I will come in and I will destroke this pump. So even with the DCV held wide open, the actuator hydraulically stalls out. It can't physically lift any more than that. It goes to zero flow. Sitting on 6,000 psi, because that's the maximum this pressure compensator will ever send to the bottom of that actuator. But the amount of flow going to it is zero, and this physically, hydraulically stalls out. You overload it, no problem. I will protect this system from overpressurizing. That's really the job of this pressure compensator. And it goes to 6,000 psi. Stops and it stalls out. So, fair enough. We get rid of a couple of bricks off this thing. if we get rid of some of the bricks off of this, then I can go right back down to saying I'm maybe only 2000 psi. And at 2000 psi, then life is good. I can move again. If I go to 2000 psi on this cylinder, yeah, I think my load shifted a little bit. So if I go to back down to 2000 psi on this load, then if I'm back down to 2000 psi on the load, then, then as far as the 2000 is concerned, then the spring wins and would shuttle this back up and start producing my maximum flow all over again. This thing is automatically making sure that I do not overpressurize this pump or system. That's how this pressure compensated valve works. And if I go back to 0, then I'll just sit 2000 psi over there. If I go to 0, I have no flow going through this DCV. No flow going here. Pump is still producing flow. So again, this has to climb all the way up to 6000 psi, and then it destrokes the pump down to that 2 degrees. So that's phase 1. As far as phase 2 is concerned, what would happen? What would happen if I just wanted to feather this DCV? And by feather it, I just want to move this actuator at, I don't know, half. Half of a pump that's capable of 100, I want to feather it down to about 50. 50 on that side. Well, there's 2000 psi over here. Is the pump capable of producing 50 liters per minute or 50 gallons per minute, as we've been talking imperial? Probably. So if I was to measure 50 coming out of that DCV, if I was to measure it going into the DCV, I might say that it probably has to be exactly the same. So pump's capable of 100, and I'm only letting 50 go through the DCV. What happened to the extra 50? And the answer lies in this understanding. So even though there's 2000 psi here, the only thing that's going to de-stroke this pump is pressure. So the pump's capable of 100, but I'm only going to use 50 of it. So there's an extra 50 gallons per minute or liters per minute, whatever. I'll use gallons. There's an extra 50 gallons per minute that would have to go somewhere. So what happens? Well, the pump produces enough flow until things will blow up, period. That means it's capable of 100, even though I'm going to restrict it down to 50 to the DCV, the only thing that would have backed it out of 100 is this pressure. So this pressure on this side of the DCV would have climbed all the way up to modify and change the stroke length, which is exactly what this pump does. As soon as I hit 6000 psi here, it actually de-strokes the pump, and it de-strokes the pump at whatever it is to maintain 6000 psi in this case. In order to maintain 6000 psi in this case, it has to be producing 50 gallons a minute approximately, and the leakage factor. But what happens is this actually will find, in this example, this will find its sweet spot at about 10 degrees, and it will maintain 10 degrees of swash plane angle, just enough flow to produce this 50 gallons a minute plus the internal leakage, because you only wanted 50 gallons per minute. So this pump will run right up to, because if I produce too much, then this pressure compensator, it says, hey, back out of it. I'll never go over 6000. So this system will run at 6000 upstream of the DCV. Meanwhile, downstream of the DCV is only load pressure. So that's okay. It's completely automated. It will find its sweet spot. If I wanted 75 here, if I open this up a little bit and wanted 75 here, then it would say, hey, obviously you want more, so I'll produce more. And it might be at 15 degrees now, and it would produce 75. It's capable of 100, so it doesn't go to full swash plate angle. It has to make sure it only produces 75. That's the scenario of a pressure compensated pump. So it's always, if you want to manipulate flow through the DCV, then this pump will do so for you. That's kind of a sweet idea, actually. An automated system built into it. It does not care about the 6,000 PSI versus maybe 0 when there's no loaded on this side, or 6,000 when there's 4,000. It doesn't care about the pressure differential across the DCV. It just requires 6,000 PSI of this pressure compensator valve in order to control that swash plate. Pressure compensator valve has one job and one job only, to make sure this does not blow up anything. And that lies probably the system. System is pretty good. As soon as I put my DCV back to that, I go to 0. That sits on 6,000, and it will now physically go back to the whole de-stroked at the whole 2 degrees all over again. And it'll just sit there, waiting to go. And it will compress this spring down, waiting. Spring's just waiting to go. So that's kind of the start of that. There's a couple things missing out of it. One of the things missing out of it is, you'll find it in the pumps based on design. What they do is they take the output oil of here, whatever this output is, and they will physically connect it clean this up a lot. They will physically connect it I don't know. They will physically connect it into that spring. So whatever this pressure here is always going to be assisting the spring. And it's part of the balancing act on it, so that when this thing is running, it's actually only the spring force that, because if I put a lot of resistance on the pump, well then that spring might be a 50-pound spring and it doesn't have enough to hold the piston on the swash plate. So we take whatever force is out here and we help it actually hold it against that swash plate, kind of the balancing act inside. But this stroking piston can still overcome this plus the outlet because of the sheer size of the stroking piston is larger, for example. Same pressure to a larger surface area means this one will win and overcome this plus the spring. And that works. So that's one of the things that's missing out of this whole explanation. Internal workings. One of the other things that is used in a pressure compensated system is what we refer to as a system relief valve. So a system relief valve is a normally closed valve, which we've already taken. Normally closed, yep, definitely normally closed. Has a spring on it, which is usually adjustable. Yep, sounds good. And it senses upstream of the valve to physically open it. In other words, these two valves are often in this system. And if you were to adjust this one up without taking into consideration this one, we can and do, because people do this all the time, we create our own problems. We create heating problems. Because a neutral standby, there should be no flow going this way. Should just de-stroke this pump. But what goes on is, if I have this set at 7,000 and I want to develop more force so I can lift more load, because we always want to lift more, then the first thing I do is I start cranking this up. And what have I done now is I start cranking this up, and I crank the spring tension up here to even this number. I don't even need to go to that number, but I'll crank this up, and magically, as I've got a gauge on this, I turn this spring in, and then suddenly spring doesn't seem to do anything. And really what's going on is all the flow is now going over this back to tank, and I start producing 100 gallons a minute over this relief valve, and we create our own heating problem. So if you're going to adjust the pressure compensator, don't forget that there's probably a system relief in there someplace. And even if I was to do this, I crank it up until, oh, it won't go up any higher. That's because this valve is already opened. And even if you, just turn it back down to, it's just starting to move things, and this valve is probably already cracked, and now you're still wasting flow over the system relief that cracked it. Maybe full flow is 7,000, but it might be 6,900 as cracking pressure. So you're wasting flow over this, which really means that you're creating heat. So if you have a pressure compensated system, there's guaranteed, there's almost every system out there has this system relief, because we would not want this pump to fail in its control system, because bad things will happen. Fine, I'll spend a little bit of money and I'll put a redundant system relief in it, and I'm happy that I protect this very expensive pump with that. But be aware, you can't just turn up this without being aware of this. So if you turn that up, then odds are you got to consider you might have to turn this up as well, just as a safe precaution. And again, take care of this, because this might be the limits of all your hoses and everything. So take care in doing some modifications is what I'm saying. If my DCV is centered, obviously this thing's doing 0. If that's got some internal leakage because they're set at the same place, then the pump is producing 10 through the system relief before it actually deswashes, and it deswashes at maybe 5 degrees, still producing that 10 gallons per minute. Bad things would happen. You would change the color on the paint or the oil at the very least. Pressure compensated system.